I start introducing, introducing this Professor Masuda. Oh, Kostya, what you're doing? Or who is doing?
I'm not doing. I will just mute.
Okay. So it's my pleasure to introduce Professor Masuda. Professor Masuda working in areas related to stochastic processes and statistics of stochastic processes. Especially, he is interested in asymptotic inference for Lévy-driven stochastic processes, in stochastic approximation, stability of stochastic processes, and related topics. And I am really pleased that he is applying a lot of stats methods to analysis of stochastic processes. And as a probabilist, he got a couple prizes of Japanese Statistical Society. And also he is active participator in many research activities related to probability and stochastic processes. Especially he is on editorial boards of several journals, and some journals where we very often publish and prize very high, like Bernoulli. So now I believe that it's time to start the talk. Professor Masuda will talk today about estimation and selection of ergodic Lévy-driven models. You are very welcome.
Thank you very much for the introduction. It's my great pleasure to have the opportunity to give this very nice series of seminars. So, as my title says, my major is about mathematical statistics for a kind of stochastic process described by a stochastic differential equation. So, among others, today I am going to talk about some statistical inference result concerned with ergodic Lévy-driven models. Well, you know, when concerned with asymptotic inference, typically, depending on the situation, it's quite crucial whether or not the model is ergodic or not. And sometimes verification of ergodicity itself might be not so easy. But today, I will also mention about quite easy to verify set of ergodicity, if I have time. Okay, so put simply, ergodicity will make somehow things simple than the non-ergodic case. Okay, so very roughly speaking, though I haven't yet given the detailed model, quite informally speaking, we'd like to do some making up some statistical circle for ergodic Lévy-driven SDE, stochastic differential equation. This is a too general picture of statistics user circle, but model setup, we are first to give a model. In our case, that's a Lévy-driven SDE. And once give a model, a statistical model, it is usually described by a family of probability measure. In our case, the family of image measures of underlying process. So once the model is mathematically fixed, we can consider estimation. Okay. Of course, depending on the objective or interest, estimation procedure or estimation way is never single. So today, one of the subsequent sections, I am going to give a brief review of existing estimation procedure. It is just one possibility, but recently I believe it to be quite practical, yet theoretically guaranteed. Okay, you will see later. And so, next, usually, once estimation procedure is given, typically, not always, but typically the step in the next step is model assessment. It cannot be a single manner. For example, testing hypothesis, a goodness of fit or lack of fit, or information criteria. So in this talk, I would like to give some recent findings about some information criteria statistics concerned with this model. Okay, so this is very rough picture. And so this is the table of contents of my talk today. Okay, in the next page, I will describe briefly the model, and which contains somehow general Lévy process. Okay, but quite generally speaking, statistics. When doing statistics, we should have some point of view. So in this talk, our motto is, well, not theoretically optimal, but the procedure is explicit and easy to implement. So this is our stance today. So after giving a very brief introduction, I would like to mention the existing result about the estimation step. And next, in the third section, though it's not published, I would like to introduce some recent findings about the formula for statistics in order to make model comparison. And then, after small simulation result, I'd like to conclude. Okay, so the objective is formally given like this. So we are given, okay, we assume that the underlying data model structure is described by this Markovian stochastic differential equation. It is, in this talk, I would like to focus on the case x and z are univariate, but it's not essential, just for simplicity of description of the result. Okay, so the point is that as a general fact, okay, so once given this model, Markovian model, and suppose that we do have some discrete time sample, sampling time point denoted by Tj here. And then typically we are going to look at likelihood. But this is not only for this model, but also for diffusion, where Z is standard Wiener process. We cannot in general write down the likelihood in closed form. So we have to resort to something computable and or approximated objective. Okay. So anyway, we formally assume that the model is sampled at equidistant sampling point with h denoting sampling step size, and capital T here denoting the terminal sampling time is assumed to diverge. So which automatically means that the long-time behavior of x will do matter when concerned with asymptotics of x. And the last one here, this is, in some sense, this is technical, but we have no idea to remove this. Currently, we have no idea to remove this condition when we try to keep the simplicity and explicit character of our forthcoming result. And the next one is statistical model. Okay. So we will assume that for the drift coefficient A and the scale coefficient C. Okay, let me mention at this stage, we are going to regard driving process Z as infinite dimensional nuisance element. Of course, Z is a Lévy process, and it will have infinite dimensional unknown parameter, namely the Lévy measure. But in this talk, it's out of our interest of estimation. It will be the next talk. Sorry, another talk. Okay, so we are given set of candidate models for coefficient. Okay, as mentioned just now, we have two objectives. And first, we have given finite family of candidates for scale coefficient. And also, similarly, we have finite many candidates for the drift. So we have in total M1 times M2 candidates. Okay. So please note that the driving process is kept unchanged all through the candidate. Okay. If not, the inferential result will not make sense too much because we are regarding Z to be nuisance parameter. Okay, so in this sense, our model is doubly indexed, one by trend parameter and the other by scale parameter. So once we fix a model index, it does depend on finite dimensional parameter of interest. Okay. Okay, so typically, if we are interested in estimation only, we will not have the index number. Just we have something like alpha x, ax alpha and cx gamma, and try to estimate alpha and gamma based on this data. But our objective in the main core section, section 3, we are given a family of model. So with this setup, we are interested in model selection. And it can be several things. It's not a universal way to make model selection. And in this talk, our interest is the so-called AIC type statistics. To the best of my knowledge, there is no previous result in this setting, with driving process being Lévy process. So as the last page of this introduction, I would like to briefly mention, just for clarity, the AIC logic. AIC is just archaic information criteria. So please forget the previous page content, and this is a general description of the logic. Okay, so the first, we are given some data whose true distribution is denoted by G. And so for that, in order to infer G, we prepare, as in the previous page, we are preparing some model. Here, just small m is just a model index. So the model of number m, we have some parameter. But based on data, we will construct some statistics for theta unknown, and then construct estimated model, also termed as prediction model. And at this stage, and in reality, maybe always, model is incorrectly specified. But as usual, we are theoretically assume that model is correctly specified, which means that for each pair of M1 and M2, we can assume the existence of true parameter. Okay, so whatever we pick Ci and Aj, the model Ij, Mij, we can pick up true parameter for which these coefficients coincide the true one. So this is the assumption of model setup. And the point is the second one. So then, in order to make a kind of model description ability, following the classical philosophy, we look at Carver-Kleibler divergence from the true distribution to the estimated model. So it is defined by this one, okay? So also terms as entropy. So this is constant, you can ignore this one. So this is not a metric, but some kind of discrepancy. So smaller value is better. So we are going to try, minimize this one. So in other words, we are going to maximize this one. So that leads to the usual maximum likelihood estimation. So this well-known AIC paradigm contains the thinking way of MLE. So the next step is once model is estimated, then so originally this is the quantity we want to look at or minimize. But we have approximated the model because we do not know G, the true distribution. If we know G, then nothing is necessary to be done. Okay, but you can look at here. In order to construct theta hat, we have, of course, made use of data. But what we want to do here is minimizing Kullback-Leibler divergence. In other words, it is some loss function related to prediction power of this model. So because of the double usage of single data set for both estimation and prediction, this measure will, this measure will have some bias. Here we denote it by B hat. So very roughly speaking, finding B hat with hopefully tractable form is the core step of doing AIC, given some model. And in our case, the model given here is Lévy-driven ST. So put simply, what we want to do is, in case of Lévy-driven ST under the ergodicity, what kind of F together with theta hat and this bias statistics could be constructed. So if for each model, we can compute this one in suitable way with, of course, with some theoretical property to be clarified, then just pick up the model M0, the index of which minimize this guy. So tractable or computable way of B hat is essential. Okay, so having this, so very briefly, having this point in hand, so let me move to the objective of this talk. Okay, so we are given some model, and so, but at the same time, we have assumed the model is sampled in discrete time, but high frequency. So this is quite a rough picture. So we have a continuous time model, but we are assuming that what we have actually observed is kind of discrete time data. So in between, we have no specific knowledge. And I should just remark, if the model can be continuously observed, in other words, if we have the whole path of blue line, then things will drastically and essentially change. Namely, for some parameter, we have no need to do statistics because of continuous time path character will enable it to identify the model, some parameter. Some of them are the case, but some of them are not. So theoretically, from a theoretical point of view, the discrete time observation or continuous time one crucially distinguish the situation. Okay, in our case, the point is how to construct estimating function. with leaving specific structure of driving process, Lévy process, as much as unknown. Okay, so the next page is, this is, let me mention some regularity condition. So the point is just, okay, so now this is our statistical model, the true one being this one. And we have set some model indices, M1 and M2, but just omitted, just for typographical ease. Okay, for each model, assumption is given like this. So the driving process is centered and standardized at time 1 in this sense. And just for, not essential, but just for simplicity of description of assumption, just we assume that the driving Lévy process is right-tailed in this sense. Okay. The second one seems messy at first glance, but it just says the global uniformly in theta global Lipschitz property of the coefficient and a kind of smoothness of each coefficient together with their derivatives. And here we also included the inverse of scale coefficient, so which means that the model, the scale part is non-degenerate. It doesn't require that C is bounded below, namely, C may, the function C may approach 0 as close as possible, but in this sense. The third one is the most important one. The title includes ergodic. So this is the condition. So there are several ways to describe stability property over a long time. But in our setting, I have decided to give this form. Okay. So just we assume the unique existence of unique invariant distribution. Okay. Not only that, but much more. So this is a so-called exponential ergodicity of Markov process. And in addition, we impose boundedness of moment in this sense. Okay. And I don't touch the full detail of the verification of the third condition, but just would like to remark easy condition for verification of this one is available. So maybe one can, for example, consult of Alex Crick's textbook published 2 or 3 years ago. And in case of this one, especially Lévy-driven Markov process, you can find this in this reference quite easy to check condition. It only involves the coefficient and the Lévy measure of Z. It does contain no probabilistic condition, just deterministic one, meaning that it's easy to check. Okay, so this is assumptions we should keep in mind, roughly. Okay, so the stepwise Gaussian quasi-likelihood estimation. This page describes how to construct estimation procedure of these 2 parameters. Okay. But it's formally it's easy to say. Okay, so this is if so this identity sign means if alpha and gamma are true value, then this differential form is equal to this integral form. And for each 2 Lebesgue integral and stochastic integrals will do some Euler type approximation. Namely, we replace the integrands by the values at the left-hand point. Here, it being tj minus 1. So, sorry, this is just a shorthand. For some function f, we use this shorthand like this. Okay, so this is just Euler approximation. Sorry. This is Euler approximation. But not only that, in our case, we have a Lévy process here. And we are thinking of a small time interval from tj minus 1 to tj, okay? Which virtually enables us to do this Euler approximation. But in addition, we need to think about this. Okay. So in general, if we do know the exact distribution of small time increment of the driving Lévy process, then maybe we could make use of it in order to construct quasi-likelihood. However, over several years, I have studied quite several concrete Lévy processes. But even if we can write down the specific distribution of this guy, it's, roughly speaking, it's not quite present in the sense that the result should be then quite model dependent. So it's far from being possible to give a unified manner result. So building on that observation, we will do quite brute approximation, which is never true. But we will introduce some asymptotic result. This brute approximation will do job. Namely, we will proceed as if the Lévy process, of course, basically non-Gaussian Lévy process is Wiener process. So which means that this terrible distributional approximation will be done. Gaussian approximation. Okay, so if this is true, it's never true in general, but assuming that this is true, then this Gaussian approximation will lead to some explicit quasi-likelihood. Because looking at this one, we can write down the one-step conditional distribution with specifying local mean and local variance. Okay. Okay, so if we keep going in this way, then it's trivial that we can write down Gaussian quasi-likelihood jointly for trend and scale. But for some technical reason, in construction of information criteria in next section, we propose here to proceed with 2 steps. Okay, so let me mention briefly. So the point is that here, the order of magnitude, stochastic order of magnitude is different. Namely, the noise part is much bigger in in short time. Namely, roughly speaking here, this is of order square root of h, while the drift is of h. So if h is quite small, the leading term should be the noise one, the scale one. But looking at this point from different perspective, this difference of orders suggests that we can ignore this drift at the first stage. So this is formally embodied like this. Okay. So this is Gaussian approximation-based quasi-likelihood with ignoring drift. So we have no drift here. If we look at the joint Gaussian approximation, here we should have drift term, but we have ignored it. So we can, well, you see that here we have no alpha. And so we can solely focus on the estimation of scale only. And we obtain some estimator, gamma hat. And in the next step, we can plug in the scale estimator, so obtained. Here, you can see here the gamma hat. So in the second step, proceeding as if we know scale part, we can focus on the estimation of trend, drift, sorry. So you see here, this is a kind of conditional least squares type. Okay. So if we, in particular, A is linear, then we can obtain explicit solution, of course. Okay, so this is just mentioning how to proceed. So the point is what theoretical property do these estimators are? Okay, to mention result, I have to impose yet another condition, namely identifiability condition, okay, which is inevitable. In order to get consistency, typically we need some argmax arguments, and in that process, we need quasi-Kalbach-Labra divergence to separate true model from the another one. Okay. So formally, it is like this, given like this. You see, this is a sort of Kalbach-Labra divergence of the variance of normal distribution. And this is the mean, Kerr divergence of the mean of Gaussian distribution. And both are typically, not typically, always non-negative. But we impose some parabola type upper bound on which the left-hand side guys can attain zero, maximum zero, only at true values. So this is identifiability, and which we cannot remove in general. I'm sorry, this is some notation page, but roughly speaking, mu k denotes the moments of Lévy measure of Z. And here are some more notation, but this is, roughly speaking, this is for describing the asymptotic covariance of our estimator. Okay, we have some integrals with respect to, sorry. We have some integrals with respect to, wait, sorry. I'm sorry, my apology. Okay. We have some integral with respect to the invariant measure, like this. This is a notation. We have something like this. But if you are familiar with the estimation of diffusion, you see some maybe familiar things. This is ingredient to describe Fisher information quantity for estimating drift. This is that for estimating scale. So anyway, everything's explicit. And this is a claim of section 2. Okay? Under the formation conditions, we can obtain asymptotic normality at rate Tn. Okay? This especially means asymptotic normality of our estimator at the rate square root of t. So we have the second item, but the point of it is that we can readily construct consistent estimate of V0, which means that we can readily estimate, construct confidence set for our estimator. Even more, we can construct then the world type testing direct to construct, and also approximate p-value can be obtained based on this asymptotic normality. Okay, this is the final page of the section 2. We can compare. Okay. So the point is that in order to estimate of our model, we just use Gaussian one. Although we presuppose that the driving noise is non-Gaussian, but it does work. But it's not, the fact itself is not quite surprising because, for example, one can think of location scale time series model, discrete time series model, for which we can make use of Gaussian quasi-likelihood and produce square root of n asymptotically normal estimator. In our setting, the flow of arguments are quite analogous. However, there is an essential difference. Okay. So, due to the stochastic behavior difference in small time of YUIMA process and of non-Gaussian Lévy process. Okay. In the limit, we have clear sharp differences. Okay, so namely, the gamma is a scale parameter in front of the noise. Okay. The estimation speed will get slower in the presence of jumps. Yet, we can obtain explicit covariance matrix. And essentially, they are different form. Okay. In case of Lévy process, we will have, in some explicit way, we have Lévy measure moments in the limit. Okay. Okay, this is the point. Okay, based on these, based on this second item, in our mind, we are going to mention constructing AIC type statistics in the next section. But before that, let me mention a few remarks, only one remark, sorry. You see, superficially, the asymptotic behavior is different. But by inspecting the proof of derivation of these two things, we can note there is a single explicit statistics. Here we denoted by SN hat, with which we have asymptotic standard normality. So this means that this guy, SN, okay? Sorry, I didn't put the explicit form of SN hat, but this guy automatically distinguishes these two different cases, okay? It is in some sense good, but in some sense not quite pleasant, because if we, suppose, for example, if we know the model is diffusion from the beginning, then we can prepare more refined statistics. So in order to make this guy work for both diffusion and Lévy, the form of SN hat is not optimal in that sense. Okay, so let's move to the next section. Okay, the point is, sorry, let me review the setting. This is a true data generating model, and for which we are going to try to fit these statistical models. with finitely many candidates. Okay. In the previous section, we have seen that we can construct estimator in each model. We have omitted the model indices, but for each pair of small m1 and m2, we can construct estimator for the unknown parameter. And we have mentioned two-stage estimation procedure in the previous section. And actually, for estimation only, it is possible to look at, this is a, say, joint quasi-likelihood. Okay, we simultaneously look at the trend, drift, and scale. It could be if our interest is only estimation. But if we also have interest of the model selection, then we should take care. Maybe I will not touch the detail, but the point is the two-stage procedure is maybe must to propose information criteria. Okay, so anyway, we have two-stage quasi-likelihood. At the first stage, we estimate trend, scale. And at that first stage, we obtain estimator. And in this section, also we select one of the scale candidates. Both will be done at the first stage. Then, after that, we have selected model for scale together with the estimator of the involved parameter. Then we move to the estimation and selection of the trend. So, this notation. Okay. So because we have mentioned the estimation steps, let me directly move to the selection point. Okay. The first stage. Once again, we focus on the scale coefficient, this one. So we need a kind of estimate of Lévy measure moment. Okay. Sorry, just to mention the point again and remember the point again. Let me go back to the page 5. So the point of construction of AIC statistics, or more specifically, the construction of bias, which corrects some bias, the bias quantity of naive estimator, the maximized quasi-likelihood. Okay, so here we need to take expectation. And of course, we will do the same thing in our setting. And so, so this is a point, the second item. So anyway, we will plug in the estimate of scale. And sorry, I haven't explained this notation, but X tilde is an independent copy of our original data. Okay. So this is quite standard in the AIC calculation. The point is that, okay, so you have here H. H is now the sampling step size going to 0. Very roughly speaking, in the investigation of Gaussian quasi-likelihood, in the presence of jumps, very roughly speaking, as you have seen, this difference of rate of convergence, we have two different resolutions in the quasi-likelihood. So which will make this factor appropriate. Okay. Typically, we do not have these two guys. Just expand this difference. And the point is here. We have something here, but this is a kind of stochastic expansion. So we have some subsequent terms. So if we look at the inside of this, the biggest parenthesis, then the leading term of this one, but this guy can diverge if k is small. This was an annoying fact in our calculation. But we can multiply h here, still keep the left-hand side going to be large order 1. Okay, but we can eliminate. Okay, so if we multiply h inside this guy, only this guy remains, and then this guy goes to 0, because now Tn tends to infinity. Sorry, this is very brief and rough explanation, but as a result, we could propose this seemingly usual AIC type statistics. But the correction term, typically this is the dimension of this parameter, namely the complexity of scale coefficient. But in our case, it's never possible to do alike. Namely, we have something model-dependent bias correction term. Okay, here mu hat, 2 mu hat are defined like this. This is quite different from just the dimension of scale, but we would like to stress that it is explicit and easy to compute. Having estimation and selection done for the scale parameter, then along with the estimation contents in the previous section, we do at the second stage drift estimation and selection simultaneously. But things are much easier. And you see, this is just the dimension of trend coefficient, which means it is just as usual AIC. Okay? But it should be noted that in our model, please recall that the driving Lévy process is non-Gaussian, basically. And for that model, we have proposed to make use of Gaussian quasi-likelihood. So it's obviously fake modeling. However, as in the case of time series modeling, Gaussian quasi-likelihood does the job. Namely, it produces the square root of t asymptotically normal estimator. But interestingly, when investigating the AIC quantity for the drift, it is given as if we are doing correctly specified model. So we need no computation to correct this bias. Namely, just we can make use of the dimension of the parameter. Okay, so important remark is that, okay, so this is already mentioned, I have mentioned, okay, due to the mixed rate structure, which means the difference of resolution of the quasi-likelihood for scale and drift, okay? Especially it is the reason which causes differences in estimating drift and, estimating scale, okay? Okay, so put simply, we have, although we have decided to use fake likelihood, it produces, even for the AIC statistics, it can make sense with explicit biases. Okay. And it should be noted that in case of diffusion, there is a previous study more than 10 years ago by Professor Uchida. He has investigated the true likelihood through Mariaban calculus. Okay. And through several Mariaban weights, and he have clarified yes, not only for drift, but also for diffusion. The usual 2 times parameter number is the correct form of AIC. Okay. But in a case, of course, it's not possible, but it is interesting to note that for drift only, we can follow the diffusion procedure, okay? Because the correction term is the same. Okay, so finally, let me mention simulations. Estimation and selection. So first, estimation. Just to produce finite sample performance, we have fixed this specific model. Here we have parameters alpha and gamma, both linear in the coefficient. So we have 2 noise. Just for comparison, we have paired standard Wiener process and normal inverse Gaussian Lévy process, symmetric and non-skew, symmetric and centered. So typically it is given by this symbol. But for the NIG Lévy process, even if we fixed it is symmetric and centered, then we have one more parameter here denoted by delta, which controls the heaviness of tails in some sense. In our case, the skewness is 0, and the force of the cumulant of the Lévy, force of the moments of Lévy measure is given by this form. So which means that delta, if delta is quite small, then non-Gaussianity degree will get increased. Okay? And especially the limit is Cauchy if delta tends to 0. So anyway, here in our setup, delta is nuisance. Please recall that in our setting, Z is nuisance. And if delta is large, it can approximate the Wiener process here. Okay. Okay, so one may wonder that if there exists noise normality test, and it does. So if you are interested, I'm very happy to see these previous works. It's not a recent one, sorry. Okay. But we have studied quite simple statistics to perform noise normality. Okay, so put simply, this is estimation performance result. The true value are minus 0.5 and 1, with delta being 5. So this column corresponds to diffusion, and this NIG part. This sense, it seems interesting that it's quite behavior quite similar, even for delta being 5. So if we set delta to be 10, then result will become much more similar. Okay. Next, let me briefly mention about the selection result. Now we change the model like this with keeping NIG noise. But we set 2 cases. This is quite close to the Wiener process, but the second one, it's skewed, and something like this. Anyway, this is centered and variance 1, having variance 1 at time 1. Okay, so satisfies our condition. So we have 4 candidates for scale and 3 candidates for drift, and conduct 10 independent trials for computing estimates. This is the first case, almost diffusion case. So the result seems reasonable in the following sense. Okay, so please first look at this direction. Okay, we have scale, four scales. Okay, in our case, the second one is most preferable in the sense that it contains the true model and at the same time the most simple one. Okay. Typical tendency and well-known tendency of our AIC statistics is that the most frequently the minimal true model is selected, but it's not that type 1 error is cannot be sorry, not type 1, but just overfitting always occur with positive probability. So even if we increase T and decrease H, the number of overfitting, okay, so this columns will not vanish. And the next, for the vertical direction, we have 3 candidates of drift. But anyway, the second one is the most preferable, and the tendency is the same. So you can focus on this column, and the middle one are to be most frequently selected, and we can see that phenomenon. The right panel indicates that, well, this is just GQAIC and formal AIC comparison. In this case, the model is, the noise is quite similar to the YUIMA process, but the resulting selection frequency are not quite the same, different from the estimation performance. But anyway, it is theoretically validated, this one, okay? This is not. Oh, sorry, maybe I said wrong thing, okay? So FAIC should not work in our setting, okay? Although the noise are quite similar to standard YUIMA process, but theoretically, asymptotically, FAIC doesn't work. The second one.
We are
yes.
out of time. Yeah.
Sorry, it's okay, the point is the same. The same tendency have been observed, and the concluding remarks. So let me mention. The point is noise does matter, but it requires care when doing some inference, and with specific difference in some correction term or formula. Okay, let me stop at this point. Sorry for a little bit use longer time. Okay, so thank you very much.
No, thank you. No, it's fine. Yeah. So we have some time for questions. Yeah. Any questions or comments? Okay, any other questions or comments?
So what happens if you have an H which isn't tending to 0? Does your procedure still deliver useful results?
Sorry, for what goes to 0?
If H does not go to 0, I mean, one of your assumptions is that you can, at least I think I understand that you can measure very high frequency data, but supposing you don't have...
Okay. I see. So, sorry, H is step size, yes. If H doesn't go to 0, then our estimation strategy doesn't work, of course, because we cannot make use of Euler approximation.
Right.
But then, as far as I know, maybe there are only some computationally intensive way can be used, such as Bayesian estimation,
ABC
which
or something.
is
Yes.
quite a simulation-based estimating way.
Right.
But so there is some trade-off between simplicity or easy to compute property and computationally heaviness or.
Right. Complexity. Yes.
But I'm sure that even for the diffusion model, Bayesian computational paradigm is still ongoing, growing area, and for Lévy process, I don't know much. Only I am a co-author of one thing, but it's quite a very particular setting. Okay, I wrote a paper about MCMC for stable Lévy-driven process, but it's quite particular.
Right. Thank you.
Okay, any other questions or comments?
Sorry, one comment. Maybe otherwise one can make use of some reduction model. And for example, for Ornstein-Uhlenbeck process driven by Lévy process, H going to 0 is not necessary, maybe in some sense, because we have a clear autoregressive structure. Okay, so but then model is quite particular. So still we have a trade-off. Okay.
Yeah.
Sorry, just a comment.
Okay, if there are no other questions or comments, then let us thank Professor Masuda again.
Thank you very much. It's my pleasure to give a talk today.
Yeah. And I believe Kostya will send